This video is a continuation of the discussion on critical points and point of inflection. So this time I'm going to teach you how to get the maxima and the minima of a function using the second derivative test. Recall that in the first derivative test, we look at the sign or how the sign of y prime or the first derivative of the function changes as the graph passes through a critical value. So just to recap what we had in the previous video. So if we have a function and its first derivative is defined in some open interval containing a critical value c, we conclude that f is a maximum at x equals c. So if f prime changes sign, changes from positive to negative through that critical value, through c. On the other hand, f is a minimum at x equals c at that particular critical value if f prime changes sign from negative to positive through that particular critical value. Alright, so we just look at the sign of f prime in the first derivative test. Now, let's go to the second derivative test. As I said, this one is easier, but it doesn't always work. It's called the second derivative test because this uses the second derivative of the function. Alright, we conclude, so f here is still a function and f prime is still defined on some open interval containing a critical value c. So we conclude that f is a maximum at c if f double prime of c. So this is the value of the second derivative of the function at the critical value c. So if f double prime of c is less than 0 or that it is a negative number, so we conclude that f is a maximum. So on the other hand, f is a minimum at c, okay, if f double prime of c is greater than 0. Now we note that the test or the second derivative test fails if we get f double prime of c equal to 0. Alright, that's why the second derivative test doesn't always work. So if we get f double prime of c, where c is a critical number, okay, so f double prime of c is equal to 0, then we cannot conclude whether c, the function is a maximum or a minimum at x equals c. So we have to go back to the first derivative test. Alright, that's why it's important that you know the first derivative test and at the same time the second derivative test, because the second derivative test is easier but it doesn't always work. So you have to go back to the first derivative test. So we'll answer the same example, but this time using the second derivative test if it can work. Alright, so let's find the critical points of the graph of the function y equals x cubed plus 3x squared minus 2. So we have to find again the critical values of the function by getting y prime and then equating y prime to 0 and then solving for the values of x from there. Alright, so y prime is equal to 3x squared plus 6x. And then equating y prime to 0 to get the critical values of the function. We get 0 equals 3x squared plus 6x, and then solving for x from this equation, we can factor out 3x from both terms on the right side, and we'll get 3x times the quantity x plus 2. Alright, so equating 3x to 0, and also x plus 2 to 0, we get two values for x, 0 and negative 2. So these are the critical values of the function. And by using the second derivative test, we would know whether these critical values will yield to a maximum or a minimum value of the function. We need to get the second derivative of the function. So if y prime is equal to 3x squared plus 6x, then y double prime is 6x plus 6. Okay, now we test x equals 0 first. So we should have the same conclusion. So x equals 0 will yield to a minimum value for y, and then x equals -2 shall lead to a maximum value for y. Okay. So what we'll do here is just look at the sign of y double prime. So if it's less than 0, then x will yield to a maxima, and if y double prime is greater than 0, then x will yield to a minima. So y double prime, what's the sign of y double prime when x is 0? So 6 times 0 plus 6. Obviously, this is positive 6. So this is greater than 0. Therefore, y is a minima, is a minimum at x equals 0. See, we had the same conclusion. And then since we want the critical point, so we need to find the y-coordinate of the minimum point whenever x is equals 0. Y is equal to 0 cubed plus 3 times 0 squared. This is from the original function minus 2. So y equals -2. So therefore, the point with coordinates 0, -2 is a minimum point. Is a minimum point. All right, we have the same conclusion, but different solution. Okay, now let's test x equals -2, the other critical value. So what is the sign of y double prime whenever x is equal to -2? We have 6 times -2 plus 6. So obviously this is -12 plus 6, so this is less than 0. So according to our rule, whenever y prime is less than 0, our conclusion would be y is a maximum. Y is a maximum at that particular value of x. So at x is equal to -2. Alright, so we have to look for the maximum point. So we have to look for the value of y whenever x is equal to -2. So from the original function, we substitute -2. So plus 3 times -2 squared minus 2. And we'll get from here y equals +2. So therefore, the point with coordinates +2 is a maximum point. Maximum point. Alright, so we obtain the same answers. So you see the second derivative test is way easier than the first derivative test. But if it happens that this becomes, so y double prime becomes equal to 0, then you cannot conclude whether x equals c will yield to a maximum or a minimum value for the function. So we have to go back to the first derivative test if that is the case. Alright, so since that function, y equals x cubed plus 3x squared minus 2, has both maximum and minimum points, automatically it contains a point of inflection. So if the graph has a maximum point, so the graph on that point is concave downwards. So, and also if the graph has a minimum point, on that point the graph is concave upwards. So somewhere in between those maximum and minimum points, the graph changes its concavity, so it has a point of inflection. So how do we find the point of inflection of the graph of the function? The first step is to find the first derivative of the function also. We already had that a while ago, so y prime is equal to 3x squared plus 6x. And then equate y prime to 0. Now we need to find the second derivative test right away. For step 2, find y double prime. So y double prime is equal to 6x plus 6. And then step 3 would be equating the second derivative to 0. So equate y double prime to 0. That is y double prime is equal to 0. So we have, since y double prime is equal to 6x plus 6, so we equate 6x plus 6 to 0. And then step 4 is to solve for x. Alright, so solving for x, we factor 6 out from 6x plus 6, so 6 times the quantity x plus 1. And then equate x plus 1 to 0 to get x equals negative 1. Alright. This must be the x-coordinate of the point of inflection, but we have to test. So step 5 is to test using the second derivative. Okay. The second derivative test for point of inflection is just like the first derivative test for critical points. The only difference is we are using the second derivative of the function. Okay, so in this case, we have to look at the changes in signs of the second derivative of the function. So if it changes from positive to negative or negative to positive, then we can conclude that this value is the x-coordinate of the point of inflection. So if y double prime does not change its sign, then we conclude that the graph doesn't have a point of inflection. Okay, but in this case, we already know that there is a point of inflection. So it must show that this is the x-coordinate of the point of inflection of the graph. So let's test. So we have to look at the value of y double prime, or the sign of y double prime, just the sign, as x passes through this candidate for the x-coordinate of the point of inflection. Alright, so we'll just have to look for the values on the right side and on the left side of negative 1, but make sure that you choose values very close to negative 1. So let's say negative 0.9 on its right and then negative 1.1 on its left. Okay, we know that y double prime is equal to 0 at x equals negative 1. So we just have to look at the sign of y double prime when x is equal to negative 1.1. So when x is equal to negative 1.1, what is the sign of y double prime? This is the function y double prime. So it's 6 times negative 1.1 plus 6. So we just want to know whether this is positive or negative, and obviously this is negative, because 6 times negative 1.1 is definitely greater than 6, so this is a negative number. Okay, less than 0. And then when x is equal to negative 0.9, what is the sign of y double prime? So it's 6 times negative 0.9 plus 6. Definitely this is greater than 0. Okay, so therefore y double prime is positive whenever x is equal to negative 0.9. Alright, so the sign of y double prime changed from negative to positive, so therefore we conclude that x equals negative 1 is the x-coordinate of the point, the only point of inflection. Let me just be very clear on that. So when y double prime changes sign from either positive to negative or negative to positive through x equals a, then we can conclude that x equals a is the x-coordinate of a point of inflection. So in this case, y double prime changed its sign from negative to positive, so therefore x equals negative 1 is the x-coordinate of the only point of inflection. Point of inflection. Okay, so we need the point of inflection, so we need its partner when x is equal to negative 1. What is the value of y? Again, we go back to the original function. Y equals x cubed plus 3x squared minus 2. So we just substitute negative 1 for x. So that's a negative 1 cubed plus 3x squared, so negative 1 squared minus 2. And we'll get from there y is equal to 0. Alright, so therefore, the point with the x-coordinate negative 1 and with the y-coordinate 0 is a point of inflection. Point of inflection. POI for point of inflection. Alright, so now we have the maximum point of the graph of the function, the minimum point also, and the point of inflection. Therefore, we can sketch the graph of the function. All right, let me have this Cartesian plane. So, and just to recall, the maximum point is at 0, negative 2 is the minimum point, and at negative 2, 2 is the maximum point. So we have these two critical points and we have this point of inflection. Let me just plot these points. The minimum point at 0, negative 2. This is the minimum point. And then the maximum point at negative 2, positive 2. Here. This is the maximum point. And then at negative 1, 0 is the point of inflection. Okay. So let's trace the curve. So from the maximum point, it goes down. Okay, from both to both directions. And then from the point of inflection, it changes concavity. So on the left side of the point of inflection, the graph is concave downwards. On the right side, the graph must be concave upwards. Okay, so something like that. Minimum point here. Minimum point, all right. Okay. There you have the graph of the function. So it's very easy to sketch the graph of a function if you can find its critical points and its point of inflection, just like this one. So there are no other critical points, so I know that the graph goes all the way down on the left side of the maximum point, and it goes all the way up on the right side of the minimum point. All right, that's it.